Okay, good morning, everyone. Okay, so we considered one important theorem. So let me consider this. Okay, so, okay, it is a little bit messy, so let me erase and let me start from the scratch. Okay, okay, now we have two vector spaces, V and W, and we have a linear mapping T from V to W. And beta is a basis for V and gamma is a basis for W space. This V and W can be anything. As we observed in the example, this V can be, say, some space of polynomials or matrices, whatever. W can be another vector space. Okay, and T is some linear mapping. Then we can express, okay, we can find some matrix A, oops, matrix A representing this linear transformation T when two bases, one basis for the domain and the other for the codomain are given. Okay, so let me draw the diagram. So we have a linear mapping T, and we have a mapping from V to W. And we have a basis beta for V, basis beta for V space, and gamma for W space. And we use the V1 up to Vn, W1 up to yes, so sorry. So this beta consists of V1 up to Vn, and gamma consists of W1 up to Wm. So V is on n-dimensional space and W is on m-dimensional space. And in that situation, we want to find A. So how do you find A? You map each vector in a basis for the domain under T. So given V1, this V1 will be mapped to some vector denoted by T over V1. And this T over V1 is a vector in W space and in which gamma is a basis. So this T over V1 can be written, T over V1 can be written as, say, A sub 1 times A11 W1 plus A21 W2 up to AM1 WM. Okay, then at that point, these coefficients A11, A21, AM1, they go to the first column of A matrix. So A11, A21 up to AM1. And then you consider the image of V2. That will be another vector in W space. So that can be written as a linear combination of the bases gamma. So A1 to W1, A2 to W2, up to AM to WM. And these A1 to A2 to up to AM2 go to the second column. So A2, A1 to A2 to up to AM to go to the second column. So in this way, you can fill the n columns of A. Then this matrix A will be denoted by T with this square bracket, and then you put beta as a subscript and gamma as a superscript. Then this is an m by n matrix, right? So that's what we get here. So as I said, each column, the first column is the coordinate of t of v1 with respect to gamma. The second column is t of v2, the coordinate of this with respect to gamma, and so on. So if you fill these n columns with those coordinates of the images of the vectors in a basis, then that will be the matrix we are looking for. And so we considered one example here, another example here. And as I said, you need to stick to the basis given. So if I modify the basis, the result will be changed. So even though, I mean, even for the same problem in example 4, if I change the basis, the matrix will be changed, right? And and given this linear transformations of T and U from V to W, we can define their sum or scalar multiple by this. So the sum of these two mapping maps any vector x to the sum of these two images, and scalar multiple of t will map x to the scalar multiple of the image vector. So if I allow such a definition, then then the then this collection of all the linear mappings from V to W will define a vector space, a much larger vector space than V or W. I'm just considering the set of mapping, set of functions. Okay, Thus, so this vector space is a set of linear transformations from V to W, and this set also satisfies the requirements for a vector space. So this vector space will be used quite often, and symbolically we will use this notation. So if you see L of V and W, that will denote the vector space of all the linear combinations from V to W. If V and W are equal, you can omit one of these and you can just use L of V. So as an example, if I consider L of P3 to P2, then I am considering all the linear combinations from P3 to P2. If I consider L of, say, R3, then it is the collection of all the linear transformations from R3 to R3. So this is this collection of all the linear mapping from R3 to R3, which is linear. or this is the collection of all the linear mapping from P3 to P2, which are all linear. So these are the definitions. We will use these notations throughout the semester. So please be familiar with this notation. And when I consider the matrices, please note that these are just matrices, right? Matrices. And the statement A in theorem 2.8 says the matrix representing T plus U will be the sum of the matrices representing T and U. So you can consider each matrix separately, or you can consider the matrix representing the sum of these two operations, of these two mappings. And scalar multiple is the same. Mm, yes, so we considered this example and those were trivial. So that's what we considered the other day, right? And then based on this, let us consider. So we considered, okay, we considered a matrix representing the linear transformation. Of course, certain bases are given for the domain and the codomain. And once they are given, we can always find a matrix. And we will use that matrix throughout the calculation, actually. So, so before we consider this, let us, okay, so if I have, if I have a linear transformation from, say, V to W, V to W, then, and if I give you some basis, say beta and gamma for V and W spaces, then we can find some matrix A, right? We can find a matrix A. Now, can I consider the converse of this? If I give you a matrix, can you think of any linear transformation from, say, given A? If I give you a matrix, then can you think of any linear transformation T from, if this is an m by m matrix, from say Fn to Fm space? Can you think of such linear transformation? Yes. How? Given, if I give you a matrix A, then when I have any vector in Fn space, I can define T of x by A times x, then this will be a linear transformation from Fn to Fm space, right? So whenever I have a matrix A, then you can think of some linear, you may regard this matrix as a certain linear transformation, right? Or if you have a linear transformation from Fn to Fm, then we can find a matrix, right? So, okay, before we consider something new, let me review the definition of the composite. Suppose that we have three sets, A, B, and C, and we have two functions, f and g. F is a mapping from A to B, and g is a mapping from B to C. So given A and B, F maps certain x to f of x. Now G is a mapping from B to C, then this f of x will be mapped to certain element, right? That's what G does. So this image, G of f of x, that is called the composite of two functions, G and f. So G of f of x is the image of f of x, and usually that is denoted by G circle f of x. So this is circle G circle f is representing this one, and that is called the composite of G and F. So for example, when a, b, c are all the real numbers and f of x is sine x and gx is x squared plus 3, then the composite of g and f will be, you first evaluate f of x and then you are looking for the image of f of x. So f of x is sine x, and then the image of sine x under g will be sine x squared plus 3. So that is the composite of G and F. If I switch the order and if you consider the composite of F and G, then that's a different story. You are looking for the image of G of X, which means you evaluate G of X first, which is x squared plus 3, and then you consider its image under the sine function. So in general, the composite of G and F and G will be different. So the commutative law is not satisfied in case of the composite function, but the associative law is satisfied. In other words, if you have one more function, say h, then h circle g circle f will be h circle g circle f, meaning you can combine g and f first and then consider the composite with h, or you can consider the composite of h and g, and then you can consider the composite with f. So as long as the order of these functions is maintained, then the associative law is satisfied. We say a function from a to b is invertible if there exists a function g from b to a such that the composite of f and g maps every vector y to itself, and also the composite of g and f also maps any element to itself. In that case, in that case, so I mean, if such function exists, then we say the function is invertible, and this function g is called the inverse of f. And usually we use this notation to describe the inverse of the function f. And we can show some properties. For example, if if a inverse exists, then it will be unique. And or the function is invertible if and only if the function is one-to-one and onto. One-to-one means two different vectors in the domain will be mapped to two different vectors in the codomain. The mapping is onto when the codomain and the range are the same. So the function is invertible if your function is one-to-one and onto. And in our linear algebra class, when U and T are linear transformations, then instead of using this U circle T, we just simply use UT to describe the composite function. So even though U and T are the names of the functions, we just simply use UT without any other symbol in between to represent the composite. Now, theorem 2.9 is interesting. If, okay, suppose that V, W, Z are vector spaces over the same scalar field F, and T is a linear mapping from V to W, and U is a linear mapping from W to Z, then this composite of U and T, okay, that is a mapping from V to Z, and that will be a linear mapping. So if you consider the composite of a linear mappings, then the result will be a linear mapping. So why is it so? So let us consider the image of ax plus y for arbitrary vectors x and y and arbitrary scalar a. Then by definition, this composite ut is evaluates ax plus y under t first, and then you map the image of ax plus y under t on, right, that is mapped under u, right? So you evaluate t of ax plus y. Now what is the t of ax plus y? Since the t is a linear mapping, t of ax plus y is a times t of x plus t of y, right? Now u is a linear mapping, so that will be, so the u maps the sum of two vectors as the sum of images. And then since U is a linear mapping, this scalar A may be multiplied after U of T of X is evaluated, right? Now U of T of X, that is just U T of X. And this U of T of Y is just U T of Y. So the result is A times U of T ut of x and ut of y. So that means ut maps ax plus y to a times ut of x plus ut of y. So this was the requirement to, right, for ut to be a linear mapping. So theorem 2.9 says the composite of two linear mappings will be a linear mapping. And actually, as I said, if I have a linear mapping, I can think of a matrix, right? So I want to consider this in terms of a matrix. But before we do that, let us check some simple facts. So suppose that T, U1, U2 are linear mappings from V to V. Please remember that this symbol denotes this is the set of linear transformations from V to V, right? So if T, U1, U2 are linear mappings, then we can easily show that this distributable law is satisfied and it is associative. And if you consider the composite with the identity mapping, nothing is changed. And scalar can be multiplied after the composite function, or that scalar can be applied to any of these two mappings. And then you can consider the composite. Either it will be fine. Okay. And in our textbook, if T is a linear mapping from V to V, then we will use this notation for the exponent, some power. So T to the 1 will denote T itself, and T squared will imply the composite of T and T. T cubed will be a composite of T squared and T, which means that is the composite T of T mapping. And in general, T to the K is defined by this. And for convenience, we will define that the zeroth power of T of any linear transformation will represent the identity mapping. Okay, as I said, I want to focus on matrices because eventually one of the reasons you study the linear algebra is that when you have a linear transformation from one vector space to another, you want to play with a matrix, not the linear transformation itself. We want to play with a matrix. Okay, so we just consider the composite or the powers of the linear transformations. So, oh, before I do that, so these powers of T, those will appear quite common if you look at some, okay, so if you came from engineering, some dynamical systems or Markov systems, or if you came from the economics, probably you heard of the Markov system. So those will be represented by these powers or the composite of T with itself. And these problems will be considered in a moment with some real actual problems. So please wait for the examples. Now, suppose that VWZ are finite dimensional vector spaces, and T is a linear mapping from V to W, and U is a linear mapping from W to Z, okay, and these T and U are linear transformations. Then moments ago, I showed that their composite is another linear transformation. And suppose that we have bases alpha, beta, gamma for these spaces V, W, and Z respectively. So alpha, V1 up to Vn is a basis for V, and W1 up to Wm is a basis for W, and gamma, Z1 up to Zp will be a basis for the Z space. Then we can easily find the matrix representing U using beta and gamma, and we can also find a matrix B representing T with respect to alpha and beta. Now we'd like to define the product of two matrices somehow so that this product represents the the linear transformation representing this composite of U and T. So please remember that I have V, W, and Z. So T is a mapping from V to W, and U is a linear transformation from W to Z. Since T is a linear transformation and since the bases are given, we can think of some matrix representing this T. And then we can find a matrix matrix representing U using beta and gamma. Now we want to define the product of between these two to define a one matrix which represents this composite. Okay. So in other words, given these two mappings, the T and U, so that we have two matrices, now I want to find a single matrix representing this composite. And moments ago, this U, the composite of U and T is a linear mapping. So there must be a matrix representing this using the basis. And basis for the domain is alpha, and basis for the codomain for this composite will be gamma. So we want to use this alpha and gamma to represent this composite as with a single matrix. That single matrix will be the definition for the product. Okay, so that's how we want to define this product. So, so if this is the matrix representing this composite, then how do we obtain this matrix? Please, moments ago, if I have V and W, when I have a T, and if alpha is a basis for V and beta is a basis for W, then how can I find the matrix A to describe, to represent this mapping T with alpha and beta? You first map, so if alpha consists of V1 up to Vn, you find the image of T of V, image of V1, and then you find the coordinate, I'm sorry, of that image with respect to beta, and that goes to the first column. Then you consider the image of the second column, the second vector of the basis. You find the coordinate with respect to beta, and using those coordinate you fill the second column of the matrix and so on. That's how we construct a matrix representing this linear transformation, right? So in order to describe the matrix, we first map the first vector of the basis, which is V1, under this composite, and then you need to find the coordinate of the vector. So once you compute this, you need to describe this vector in terms of gamma to get the appropriate coefficient. So let us think about this image. So the image of Vj under Ut is the, you first consider the image of Vj under T, and then you will map this to something under U mapping, right? Now, please remember T of Vj, how do you find the T of Vj? What is this? What is the coordinate? What is the T of Vj? If this is your matrix A, okay, then the first column is the coordinate of beta, coordinate of T of V1. That means the first column, okay, so 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 for example, T of V1 beta is, for example, say 1, 2, 3 up to M, where beta consists of W1 up to Wm. What does that mean? That means T of V1 will be 1 times the W1 plus 2 times the W2 up to M times the WM, because this 1, 2 up to m will be the coefficient, the coordinate of the image vector with respect to beta basis. So in order to construct T of V1, I need to consider this linear combination with a basis vector, right? So to find the T of Vj, I need to extract the coefficients. The coefficients are, so here, coefficients are, since this is Vj, jth column of B matrix. So the jth column of B will be the coefficients of this linear combination. Please remember here, when these numbers are the coefficients, then T of V1 can be constructed by this linear combination using this as coefficients. And this, if this is the coordinate for T of V1, then that is the first column of this A matrix, right? Now, in this case, I am considering the image of T of Vj, and B is the matrix representing this T. So T of Vj can be constructed as a linear combination of the bases using the jth column of the B matrix. So that's why we have this linear combination of bases, the beta. Now, now U is a linear transformation. So U of certain linear combination can be computed by the linear combination of U of WK. Okay. Now, what is U of WK? Okay, that is the, how can I construct this one? Hmm? By the same reasoning, you need to consider the kth column of A matrix, and then you can consider the linear combination with respect to gamma, and these, using these numbers as the coefficients. So eventually we get this expression. Now, since this is two summations, you can switch these two summations in K and summations in I. Then you get two summations in the different order. I just switched these two summations. And since AIK, BKJ, JI are, they are all, I'm sorry, AIK and BKJ are numbers. So please remember, BKJ and AIK are numbers. So I can just multiply those numbers, and then you have this ZI vector. Okay, then what does that mean? I am, this UT is a composite function from V to Z space, and UT is the mapping from V to Z, and alpha is a basis for V, and gamma is the basis for Z, and the matrix representing this composite will be filled with some columns, and each column is the coordinate of each vector of alpha under this composite UT when gamma is used as a basis for Z space, right? So here I am sending this Vj under UT, and I have now some expression with respect to zi's. So this will be the coefficient. Those will go to the ith column. So these are the ith column entries of this matrix for the composite UT from with alpha and gamma. So those are the ith column entries. So in particular, okay, so if I, oh no, yeah, so that is the ith column entries, right? So when I is 1, that this expression represents the first row ith, I'm sorry, so, sorry, no, 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 no. Yes, no, no, just a second, just a second. This is the, oh, sorry, this is the image of Vj, so this is not ith but jth column entries. So when I is 1, the first row jth column entry will be, so this is the ith row jth column entry of this matrix. So in other words, if if I fill the ith row jth column of this matrix with this expression, then, so in other words, so if some C matrix is constructed with C sub ij, with C sub ij is defined by A sub I I k goes 1 to m. So k goes from 1 to m, ai k, and b k j. So if I fill the ith row jth column with this number, then this C will be the matrix representing this composite, right? So that's how we want to define the product of two matrices. So given some m by m matrix A and n by p matrix B, we define the product of this A and B to construct an m by p matrix whose ith row jth column entry is given by this expression. So meaning if I have a matrix which is an m by n matrix, m rows and n columns, and if I have a B matrix with n rows and p columns, then the product will be an m by p matrix whose ith row jth column entry is obtained by multiplying the ith row entries of A. So as k goes from 1 to n, aik represents the ith row entries of A, and bkj represents the jth column entry of a B matrix. So that is the jth row of the A matrix, and here is the, I'm sorry, the ith row of A and jth column of B entries, those are multiplied, and added. The final result will go to the ith row and jth column. So that's how we define the two matrices, and that will be called the product of A and B. And then we will simply use this notation. Okay. So that is the definition. So in order to find the ith row jth column entry of this product, I need to multiply the entries of the in the ith row of A matrix and the jth column entries of a B matrix. So in order to define this value, the number of entries in the ith row of A must be the same as the number of entries in the jth column of B matrix. So note that in order to define the number of entries in the ith row of A must be the same as the number of entries in the jth column of B matrix, and the number of entries in the ith row of A is, so that is the number of columns, and the number of entries in the jth column of B is just number of rows of B matrix. So in order to define A times B, so in order to define A times B, number of columns of the first matrix must be the same as the number of rows of the second matrix. So if I have these two matrices, 1 to 1, 0, 4, negative 1, and 4 to 5 matrix, you first consider the first row of the first matrix multiplied by this 4 to 5. This product will go to the first row, first column. When the second row of the first matrix is multiplied to the vector, the 4 to 5, that entry go to the second row, first column entry. And as I said, this is a 2 by 3 matrix and 3 by 1 matrix. So these three must match. Then the result will be 2 by 1 matrix. So 2 by 3 times 3 by 1 will give you 2 by 1 matrix. Oh, just for your information, there are many ways to define the product of two matrices. Okay, and this definition is just one of many different kinds. Okay, there are many ways to define the product of two matrices. So if you came from physics, then probably you may heard of some Einstein product. And if you came from say engineering department, then you have different say. Okay. So product. So there are many ways to define the product. And in our class, in our textbook, the one, okay, showing, okay, in this slide is just the definition of the product of two matrices. And for that definition, I need this property for this definition. Some other definition of the product may require different requirements. But anyway, that's the one we are going to use in this class. Now, when I multiply these two matrices in that order, you get this one. But if I switch the order of two matrices, you get different matrix. So in general, commutative law does not hold. And actually, we can consider this example one more time, because in this case, A times the B constructs this vector. The problem occurs when I try to multiply B and A, because B is a 3 by 1 matrix and A is 2 by 3 matrix. So the number of columns of the first matrix does not match the number of rows of the second matrix. So this one cannot be defined. This one cannot be defined. So even though you can define the product A times B, that does not mean that we can define B times A. Okay. So in these two matrices, A times B exists, but B times A does not exist at all. So they cannot be the same. Now, in case, please remember that we consider the transpose. What was the transpose? Transpose was constructed by sending all the columns to the rows. All right. Now, if I consider the I throw jth column entry of this transpose of the product, then by definition of the transpose, the I throw jth column entry of this product will be jth row ith column entry of the original product AB, and jth row ith column entry of this product is obtained by considering the product between jth row of the first matrix times the ith column of the second matrix. So we get this one. Now let me consider the ith row jth column entry of this product. And please remember, if A times B can be defined, in other words, if A has n columns and if B has n rows, then B transpose will be P by n matrix and A transpose will be an n by m matrix. So the number of columns of the first matrix and the number of rows of the second matrix match. So we can define B transpose times A transpose. And as I said, even though we can multiply A times B, that does not mean we can define B times A. But anyway, we can consider B transpose times A transpose. So the ith row jth column entry of this will be the ith row entries of the first matrix multiplied by the jth column entry of the second matrix, and then you need to add them. Now, ith row kth column entry of B transpose will be the kth row ith column entry of B, And kth row jth column entry of a transpose will be jth row kth column of a matrix. And now these two numbers are scalars. So in case of the scalars, they commute. So these two are the same, meaning the ith row jth column entry of the transpose of A times B will be ith row jth column entry of B transpose times A transpose. In other words, we have this result. The transpose of a product is the product of the transpose in the opposite order. So please remember this. So as I said, we defined the product of two matrices as above in order to derive the following identity. Okay, so when T and U are linear transformations from V to W and U to Z and W to Z, then their composite will have a matrix representation, and that matrix representation will be the product of these two matrices representing U and T respectively. And please remember, you cannot switch the order. Not okay, because the matrix multiplication is not commutative. So you need to be careful with the order of the matrices. So here is an example. So suppose that U represents a linear transformation differentiation. And let me consider this mapping from P3 to P2. We observe that this is a linear transformation, right? And T is a linear transformation from P2 to P3. And now I want to consider the integration. And for simplicity, let me use the standard order basis for P3 and P2. So alpha consists of 1 x squared and x cubed. And beta consists of 1 x squared. We previously found the matrix for the differentiation. So let me just consider the matrix for T only today. So to find the matrix for T, okay, I need to consider the image of 1 under T. So that means I need to integrate one function from 0 to x. So you need to find the antiderivative of 1 and evaluate this at 0 and x and consider their difference. So x minus 0, which is x, right? So x is 0 times 1 plus 1 times x plus 0 times x squared plus 0 times x cubed. So the weights are 0, 1, 0, 0. So 0, 1, 0, 0 appears in the first column of the matrix for T. And then if I consider T of x, then I need to consider the image of T, and on antiderivative of T is 1/2 of T squared. So you get 1/2 of x squared minus 0. So that is 0 times 1 plus 0 times x plus 0, not 0, but 1/2 times x squared plus 0 times x cubed. So the coefficients are 0, 0, 1/2, 0. 0, 0, 1/2, 0. Go to the second column. And t of oops, t of x squared will be t squared is integrated from 0 to x. So you evaluate 1/3 of t cubed at 0 and x, and you get 1/3 of x cubed. So that is 0 times 1 plus 0 times x plus 0 times x squared plus 1/3 times x cubed. So these four numbers, 0, 0, 0, 1/3, go to the third column of T matrix. So given these two matrices, the composite has the matrix. Now, for this, the matrix for the composite, you can apply the composite, or you can just multiply these two. If you multiply them, you get the matrix representing this composite. And in case of the matrix multiplication, we can easily prove that matrix multiplication satisfies this distributive law. Okay, and we also learned that it is associative, and scalar may be multiplied at any point in the calculation. Identity matrix does not alter the entries of the matrix A. Then, what is the statement D? If V is an n-dimensional vector space with an ordered basis beta, then identity mapping with respect to beta will be the identity matrix. It is true. So here beta can be any basis, with any basis. So for example, let us consider, say, a P2 space with beta given by 1, 1 plus x, and 1 plus x squared. Then identity mapping will map 1 to 1 and 1 plus x to 1 plus x and 1 plus x squared to 1 plus x squared. So this 1 is 1 times 1 plus 0 times 1 plus x plus 0 times 1 plus x squared. And 1 plus x is 0 times 1 plus 1 times 1 plus x plus 0 times 1 plus x squared. And 1 plus x squared is 0 times 1 plus 0 times 1 plus x plus 1 times 1 plus x squared. So the matrix will be 1, 0, 0, 0, 1, 0, 0, 0, 1, which is the identity matrix. So that is the matrix representing this identity mapping with respect to beta, and that equals the identity matrix. So these are some properties of the matrix multiplication, and as I said, please remember, and first, if A times B C can be multiplied, that will be A times B times C, so that the matrix multiplication is associative. but matrix multiplication is not commutative. And you can check this proof. It is simple. Now, if and given I can, so this corollary just extends the distributive law. So in the theorem, we considered just the two matrices, but now suppose that if I have k matrices, then their linear combination multiplied by A will be a linear combination of this product. So as long as the order of the matrices is maintained, so please, as I said, this order is very important in matrix multiplication. So you need to maintain the order. You okay? So you cannot switch BI and A. Okay, you need to keep that order A and BI in that order. Then you can derive this distributive law. And moments ago, we considered this for n by m matrix A. We defined these powers of A, right? Given this A matrix, if you multiply A with A itself, you get zero matrix. So this one does not mean A is zero. And the cancellation law does not hold. So for example, A times A will be the zero matrix, as I said, and A times the zero matrix will be also zero matrix. Okay? So A times B and A times C are equal. That does not mean B and C are equal. So you cannot have the cancellation law. So this cancellation law does not hold in general. Okay. So this is important property of the matrix, and the same thing, the previous one, the A squared. A times the B equals to zero does not mean A is the zero or B is zero matrix. So we have these two. Okay, so these cancellation law do not hold. Please be careful. Okay, and theorem 2.13 says if suppose that A is an n by m matrix and B is an n by p matrix and excuse me, let me review what I just mentioned. So when I say A times B, when I define this product, A times the ith row jth column of this A times B is AIK BKJ, where K goes from 1 to N. Okay. So that's the ith row jth column entry of this product. So, so given A matrix and B matrix, here is the product, A times B. So to obtain the first column of A times B, you multiply the entries in A with first column of a B matrix. So please remember that the first row of A times B, the first column of B will define the first entry of this A times B. If I consider the product between the second row of A with B, you get the second entry of this column A times B. And third row of A times the first column of B will give you the third entry of this product. So if I call the first column of B by B sub 1, okay, then this first column of A times B is A times B1, will be the first column of this product. If I consider second column of B, and if I call this guy as a B2, then when you multiply each row of A with B2, you get the entries in the second column of A times B. So the second column is obtained by multiplying A with B2. Okay. So in other words, when A when A is multiplied by some B matrix, and if B has B1, B2 up to B sub P, then this product will be A times B1 becomes the first column of the product. A times B2 will be the second column of the product. And A times BP will be the pth column of the product. So if you construct a matrix with this, then we get this equation. So the property A in theorem 213 just implies that one. So if Uj denotes the jth column of the product and Vj denotes the jth column of a B matrix, then A times Vj will be the jth column of this product, as I said. Okay. So that's the first claim. And the second part, the B times Ej, so yeah, and when I multiply B with E sub j, you get Vj. What is the Vj? Vj is the jth column of the B matrix. So why is it so? We can use this one, this idea. B times the identity matrix will be B. So the columns are of the B matrix is B, V1 up to VP is B times identity E1, E2 up to EP. And that is, as I said, as in A, B times E1, B times E2, and so on. So B times E1 will be V1, B times E2 will be V2, and so on. So the proof is simple. So anyway, we just considered the definition of the product of between two matrices, and we observed some properties of those. So please be familiar with this, because we will sometimes consider the product of some composite of the linear transformations in terms of the matrix multiplications. Okay, so we will interpret some linear transformation in terms of a matrix. Okay, so please be familiar with the matrix and its properties. Okay, thank you for listening, and see you next time.